Software testing is carried out at different levels through the entire software development lifecycle. There are many strategies that can be used to test software. A testing strategy that is chosen by most software teams is it takes an incremental view of testing, beginning with testing of individual program units, moving to tests designed to facilitate the integration of the units, and culminating the tests that exercise the constructed system. Each of these classes of tests can be described as unit testing, integration testing, functional testing, system testing, acceptance testing, etc. Let me briefly describe each of these testing. In unit testing, test cases verify the implementation of design of each software element. Integration testing traces detailed design and architecture of the system. Hardware and software elements are combined and tested until the entire system has been integrated. Functional test. It is used to exercise the code with the common input values for which the expected values are available. In system testing, it checks for system requirements. And finally, in acceptance testing, it determines if test results satisfy acceptance criteria of project stakeholders. Now let us discuss in detail about these different types of testing. Unit testing. Unit testing focuses verification effort on the smallest unit of software design, the software component or module. Using the component level description as a guide, important control paths are tested to uncover errors within the boundary of the module. The relative complexity of tests and uncovered errors is limited by the constrained scope established for unit testing. The unit test is white box oriented and the step can be conducted in parallel for multiple components. Unit test considerations. The module interface is tested to ensure that information properly flows into and out of the program unit under test. Module interface can be local data structures, boundary conditions, independent paths, or error handling paths. The local data structure is examined to ensure that data stored temporarily maintains its integrity during all steps in an algorithm's execution. Boundary conditions are tested to ensure that the module operates properly at boundaries established to limit or restrict processing. Basis paths or all independent paths through the control structure are exercised to ensure that all statements in a module have been executed at least once. And finally, all error handling paths are tested. So, test cases are designed for all these types of data structures, boundary conditions, basis paths, and error handling paths. Selective testing of execution paths is an essential task during the unit test. Test cases should be designed to uncover errors due to erroneous computations, incorrect comparison, or improper control flow. Types of errors commonly found during unit testing are misunderstood or incorrect arithmetic precedence, mixed mode operations, incorrect initialization, or precision inaccuracy. Unit testing is normally considered as an adjunct to the coding step. Once the source code has been developed, reviewed, and verified for correspondence to component level design, unit test case design begins. A component is not a standalone program. Driver or step software must be developed for each unit test. In most applications, a driver is nothing more than a main program that accepts test case data, passes such data to the component, and prints relevant results. Steps serve to replace modules that are subordinate the component to be tested. A step or dummy subprogram uses the subordinate modules interface, may do minimal data manipulation, prints verification of entry, and returns control to the module undergoing testing. Drivers and steps represent overhead. That is, both are software that must be written. Formal design is not commonly applied, but that is not delivered with the final software product. If drivers and stubs are kept simple, actual overhead is relatively low. Unfortunately, many components cannot be adequately unit tested with simple overhead software. In such cases, complete testing can be postponed until the integration test step. Integration testing. Unit testing that otherwise seem to be working fine individually as units but start causing problems when integrated together. The problem, of course, is putting them together, that is, interfacing. Data can be lost across an interface. One module can have an inadvertent adverse effect on another subfunctions. Subfunctions, when combined, may not produce the desired major function. Individually acceptable imprecision may be magnified to unacceptable levels. Global data structures can present problems. Sadly, the list goes on and on. Integration testing is a systematic technique for constructing the software architecture while at the same time conducting tests to uncover errors associated with interfacing. The objective is to take unit tested components and build a program structure that has been dictated by design. There is often a tendency to attempt non-incremental integration. Non-incremental integration or Big Bang approach combines all the components at the same time and then tests the program on the whole. This approach gives a number of errors that are difficult to isolate and trace as the whole program now is very vast. The correction of such errors seem to go into infinite loop. Incremental integration is the opposite of Big Bang approach. The program is constructed and tested in small increments where errors are easier to isolate and correct. Interfaces are more likely to be tested completely, and a systematic test approach may be applied. So let us discuss two different incremental integration strategies: top-down integration and bottom-up integration. Top-down integration. Top-down integration testing is an incremental approach to construction of program structure. Modules are integrated by moving downward through the control hierarchy, beginning with the main control module, that is main program. Modules subordinate and ultimately subordinate to the main control module are incorporated into the structure in either a depth first or breadth first manner. Now in this figure of top-down integration, depth first integration integrates all components on a major control path of the program structure. Selection of a major path is somewhat arbitrary and depends on application specific characteristics. For example, selecting the left hand path components M1, M2, M5 would be integrated first. Next, M8, or if necessary for proper functioning of M2, M6 would be integrated. Then the central and right hand control paths are built. Breadth first integration incorporates all components directly subordinate at each level, moving across the structure horizontally. From the figure, components M2, M3, M4 would be integrated first. The next control level, M5, M6, and so on follows. The integration process is performed in a series of 5 steps. The integration process is performed in a series of 5 steps. These are the steps for top-down integration. 1. The main control module is used as a test driver and steps are substituted for all components directly subordinate to the main control module. 2. Depending on the integration approach selected, that is depth or breadth first, subordinate steps are replaced one at a time with actual components. 3. Tests are conducted as each component is integrated. 4. On completion of each set of tests, another step is replaced with the real component. And 5. Regression testing we will discuss later in this section. Regression testing may be conducted to ensure that new errors have not been introduced. The process continues from step 2 until entire program structure is built. Top-down strategy sounds relatively uncomplicated, but in practice, logical problems can arise. So another incremental integration strategy is bottom-up integration. Bottom-up integration testing, as its name implies, begins construction and testing with atomic modules, that is, components at the lowest level in the program structure. Because components are integrated from bottom up, processing required for components subordinate to a given level is always available and the need for steps is eliminated. A bottom-up integration strategy may be implemented with the following steps. 1. Low-level components are combined into clusters, sometimes called builds, that perform a specific software subfunction. 2. A driver, a control program or testing, is written to coordinate test case input and output. 3. The cluster is tested. 4. Drivers are removed and clusters are combined, moving upward in the program structure. So these 4 steps are used for bottom-up integration. Important key point is that bottom-up integration eliminates the need for complex steps. Integration follows the pattern illustrated in this figure. Components are combined to form clusters 1, 2, and 3. Each of the clusters is tested using a driver shown as dashed block. Components in clusters 1 and 2 are subordinate to MA. Drivers D1 and D2 are removed and the clusters are interfaced directly to MA. Similarly, driver D3 for cluster 3 is removed prior to integration with module MB. Both MA and MB will ultimately be integrated with components MC and so forth. As integration moves upward, the need for separate test drivers lessens. In fact, if top 2 levels of program structure are integrated top down, the number of drivers can be reduced substantially and integration of clusters is greatly simplified. Regression testing. It is an important strategy for reducing side effects. Each time a new module is added as part of integration testing, the software changes. New data flow paths are established, new input-output may occur, and new control logic is invoked. These changes may cause problems with functions that previously worked flawlessly. In the context of an integration test strategy, regression testing is the re-execution of some subset of tests that have already been conducted to ensure that changes have not propagated unintended side effects. Regression testing is the activity that helps to ensure that changes due to testing or for other reasons do not introduce unintended behavior or additional errors. Regression testing may be conducted manually by re-executing a subset of all test cases or using automated capture or playback tools. Capture or playback tools enable the software engineer to capture test cases and results for subsequent playback and comparison. The regression test suite contains 3 different classes of test cases. a representative sample of tests that will exercise all software functions, additional tests that focus on software functions that are likely to be affected by the change, tests that focus on software components that have been changed. As integration testing proceeds, the number of regression tests can grow quite large. Therefore, the regression test suite should be designed to include only those tests that address one or more classes of errors in each of the major program functions. It is impractical and inefficient to re-execute every test for every program function once a change has occurred. Smoke testing is an integration testing approach that is commonly used when product software is developed. It is designed as a pacing mechanism for time-critical projects, allowing the software team to assess the project on a frequent basis. In essence, the smoke testing approach encompasses the following activities. 1. Software components that have been translated into code are integrated into a build. A build includes all data files, libraries, reusable modules, and engineered components that are required to implement one or more product functions. 2. A series of tests is designed to expose errors that will keep the build from properly performing its function. The intent should be to uncover showstopper errors that give the highest likelihood of throwing the software project behind schedule. 3. The build is integrated with other builds and the entire product in its current form is smoke tested daily. The integration approach may be top down or bottom up. The daily frequency of testing the entire product may surprise some readers. However, frequent tests gives both managers and practitioners a realistic assessment of integration testing progress. Now let us discuss what benefits can be derived from smoke testing. Smoke testing provides a number of benefits when it is applied on complex, time-critical software engineering projects. 1. Integration risk is minimized because smoke tests are conducted daily. Incompatibilities and other showstopper errors are uncovered early, thereby reducing the likelihood of serious schedule impact when errors are uncovered. 2. The quality of the end product is improved because the approach is construction oriented. Smoke testing is likely to uncover functional errors as well as architectural and component level design errors. If these errors are corrected early, better product quality will result. Error diagnosis and correction are simplified. Like all integration testing approaches, errors uncovered during smoke testing are likely to be associated with new software increments. That is, the software that has just been added to the build is a probable cause of a newly discovered error. 4th, progress is easier to assess. With each passing day, more of the software has been integrated and more has been demonstrated to work. This improves team morale and gives managers a good indication that progress is being made. Validation testing or acceptance testing. Validation testing begins at the culmination of integration testing. When individual components have been exercised, the software is completely assembled as package and interfacing errors have been uncovered and corrected. At the validation or system level, the distinction between conventional software, object oriented software, and web app disappears. Testing focuses on user visible actions and user recognizable output from the system. Validation succeeds when software functions in a manner that can be reasonably expected by the customer. Software validation is achieved through a series of black box tests that demonstrate conformity with requirements. This is to ensure that all functional requirements are satisfied, all behavioral characteristics are achieved, all performance requirements are attained, documentation is correct, and other requirements are met. It is virtually impossible for a software developer to foresee how the customer will really use a program. When custom software is built for one customer, a series of acceptance tests are conducted to enable the customer to validate all requirements. Conducted by the end user rather than software engineers, an acceptance test can range from an informal test drive to a planned and systematically executed series of tests. It is virtually impossible for a software developer to foresee how the customer will really use a program. Instructions for use may be misinterpreted, strange combinations of data may be regularly used, output that seemed clear to the tester may be unintelligible to the user in the field. So alpha and beta testing. The alpha test is conducted at the developer side by the customer. The software is used in a natural setting with the developer looking over the shoulder of the user and recording errors and usage problems. Alpha tests are conducted in a controlled environment. Then beta test is conducted at one or more customer sites by the end user of the software. Unlike alpha testing, the developer is generally not present. Therefore, the beta test is a live application of the software in an environment that cannot be controlled by the developer. The customer records all problems that are encountered during beta testing and reports these to the developer at regular intervals. As a result of problems reported during beta tests, software engineers make modifications and then prepare for release of the software product to the entire customer base. System testing. System testing is actually a series of different tests whose primary purpose is to fully exercise the computer-based system. Software is incorporated with other system elements, example, hardware, people, information, and a series of system integration and validation tests are conducted. System testing is actually a series of different tests whose primary purpose is to fully exercise the computer-based system. Although each test has a different purpose, all work to verify that system elements have been properly integrated and perform allocated functions. The different tests under system testing are recovery testing, security testing, stress testing, and performance testing. So let us discuss these types of system tests for software-based systems. Recovery testing. Many computer-based systems must recover from faults and resume processing with little or no downtime. In some cases, a system must be fault tolerant, that is, processing faults must not cause overall system function to cease. In other cases, a system failure must be corrected within a specified period of time or severe economic damage will occur. Recovery testing is a system test that forces the software to fail in a variety of ways and verifies that recovery is properly performed. If recovery is automatic, that is performed by system itself, reinitialization, checkpointing mechanism, data recovery, and restart are evaluated for correctness. If recovery requires human intervention, the mean time to repair MTTR is evaluated to determine whether it is within acceptable limits or not. Security testing. Any computer-based system that manages sensitive information or causes action that can improperly harm individuals is a target for improper or illegal penetration. Penetration spans a broad range of activities. Hackers who attempt to penetrate systems for sport, disgruntled employees who attempt to penetrate for revenge, dishonest individuals who attempt to penetrate for illicit personal gain, etc. Security testing attempts to verify that protection mechanism built into the system will in fact protect it from improper penetration. During security testing, the tester plays the role of the individual who desires to penetrate the system. Anything goes. The tester may attempt to acquire passwords through external clerical means, may attack the system with custom software designed to break down any defenses that have been constructed, may overwhelm the system, thereby denying service to others, may purposely cause system errors, hoping to penetrate during recovery, may browse through insecure data, hoping to find the key to system entry, etc. Given enough time and resources, good security testing will ultimately penetrate a system. The role of the system designer is to make penetration cost more than the value of the information that will be obtained. Stress testing. Stress tests are designed to confront programs with abnormal situations. Stress testing executes a system in a manner that demands resources in abnormal quantity, frequency, or volume. Special tests may be designed that generate 10 interrupts per second when 1 or 2 is the average rate. Input data rates may be increased by an order of magnitude to determine how input functions will respond. Test cases that require maximum memory or other resources are executed. Test cases that may cause thrashing in a virtual operating system are designed. Test cases that may cause excessive hunting for disk resident data are created. Essentially, the tester attempts to break the program. Variation of stress testing is a technique called sensitivity testing. Sensitivity testing attempts to uncover data combinations within valid input classes that may cause instability or improper processing. Performance testing. For real time and embedded systems, software that provides required function but does not conform to performance requirements is unacceptable. Performance testing is designed to test the runtime performance of software within the context of an integrated system. Performance testing occurs throughout all steps in the testing process. Even at the unit level, the performance of an individual module may be assessed as tests are conducted. However, it is not until all system elements are fully integrated that the true performance of a system can be ascertained. Performance tests are often coupled with stress testing and usually require both hardware and software instrumentation. That is, it is often necessary to measure resource utilization like processor cycles in an exacting fashion. Software debugging is not testing. It often offers as a consequence of testing. Why is debugging so difficult? In all likelihood, human psychology has more to do with an answer than software technology. However, a few characteristics of bugs provide some clues. The symptom may disappear when another error is corrected. Sometimes the symptom and the cause may be geographically remote. Sometimes the symptom may actually be caused by non-errors, for example, round-off inaccuracies. Sometimes the symptom may be caused by human error that is not easily traced. For example, wrong input wrongly configured the system, such cases. Sometimes the symptom may be a result of timing problems rather than processing problems. For example, taking so much time to display results. It may be difficult to accurately reproduce input conditions. For example, a real-time application in which input ordering is indeterminate. The symptom may be intermittent. This is particularly common in embedded systems that couple hardware and software inextricably. The symptom may be due to causes that are distributed across a number of tasks running on different processors. Brain Kernighan says everyone knows that debugging is twice as hard as writing a program in the first place. As the consequences of an error increase, the amount of pressure to find the cause also increases. Often, pressure forces some software developers to fix one error and at the same time introduce two or more errors. Code inspection is a formal technical review. It is a software quality control activity performed by software engineers or others. The most formal review type, which is a kind of static testing, to avoid the defect multiplication at a later stage is code inspection. An code inspection report lists the findings, which include metrics that can be used to aid improvements to the process as well as correcting defects in the document under review. Regardless of the formal technical review format that is chosen, every review meeting should abide certain constraints such as between 3 and 5 people should be involved in the review and duration of the review meeting should be less than 2 hours. For every code inspection meeting, preparation before the meeting is essential, which includes reading of any source document to ensure consistency. Inspections are often led by a trained moderator who is not the author of the code. The inspection process is the most formal type of review based on rules and checklists and makes use of the entry and exit criteria. Code inspection usually involves peer examination of the code, and each one has a defined set of roles. After the meeting, a formal follow-up process is used to ensure that corrective action is completed in a timely manner. There are several code review mechanisms: informal code review, walkthrough code review, technical review, and inspection method. The topic that we have discussed, that is code inspection, is the main highest level of formal method of code review meeting. The main purpose of code inspection is to find defects formally, and it can also support any process of improvement, if any, in the formal way. Code walkthrough is a form of peer review in which a programmer leads the review process and the other team members ask questions and spot possible errors against development standards and other issues. The meeting is usually led by the author of the document under review and attended by other members of the team. Review sessions may be formal or informal. Before the walkthrough meeting, the preparation by reviewers and then a review report with the list of findings will be included. The scribe, who is not the author, marks the minutes of the meeting and note down all the defects or issues so that it can be tracked to closure. The main purpose of walkthrough is to enable learning about the content of the document under review, to help team members gain an understanding of the content of the document and also to find defects. Technical reviews may be quite informal or very formal and can have a number of purposes but not limited to discussion, decision making, evaluation of alternatives, finding defects, and solving technical problems. This figure shows the level of formality for the code walkthrough. You can see the difference of the formality of walkthrough activity and code inspection activity, and thus we can understand the level of formality involved with these different types of activities. The main purpose of walkthrough is to enable learning about the content of the document under review, to help team members gain an understanding of the content of the document and also to find defects.